Okay, so the last talk of this session is by Fredrik Dahlqvist on semantics of higher order probabilistic programs with conditioning.
Good morning. Is this working? Yeah. Okay. So this is joint work with Dexter Cozen, the great Dexter Cozen, who in 1981 pretty much founded the topic of semantics of probabilistic programming languages with a paper. And this paper is very much in the vein of that original paper. It uses the very same kind of maths. However, it's quite a dense paper mathematically. So I'm going to just highlight the key ideas with a minimal, simple example. And I won't delve into the maths, and I'll refer you to the paper for that. But I'm going to talk about higher order, and I'm going to talk about conditioning. Okay. Okay, so this is the minimal example I could think of that highlights all the features I want to highlight. And it's a probabilistic full adder. So it's a little binary system which takes two inputs A and B, 2 bits, and performs their sum, returns it at S with a carry. And the third input I'm going to take as a probabilistic input. So in fact, I'm considering this as a 2-bit, 2-bit to 2-bit system. And the control is a Bernoulli distribution, which you don't know. Okay, so as a probabilistic program, this is what it looks like. The only probabilistic thing in this program is the sample, and I'm sampling from a mystery Bernoulli distribution. And it returns the sum and the carry. Okay. So the semantics of this program is this Markov chain. Because I don't know the mystery Bernoulli distribution, I'm going to use P for the probability of 1 and Q for 1 minus P. And you've got this transition system, OK? So this is a very standard way of looking at this program. Now, mathematically, it could be written as this, in this monad style with the distribution monad. So it's a coalgebra or a Kleisli arrow, which to each state associates a distribution of the successor state. So it's a very standard way of looking at things. The other very standard, so this is a very PL way of looking at things. And the other very standard way of looking at things is the probabilistic or mathematician way of looking at things, which is a stochastic matrix. So it's an operator which takes as input a distribution on the initial state and outputs a distribution on the output states. Okay, so for example, I'm going to use the conventions that all vectors are column vectors. So it's a column stochastic matrix. Okay, and these two formalisms are completely equivalent because if you know what one is doing, you can work out the other and vice versa. But from my perspective, at least, I like the fact that linear algebra has 200 years of history, and geniuses like Gauss and people like that churning out loads of really cool, deep, interesting results that I'm not going to work out for myself in my lifetime. And there's also 70 years at least of implementation. So the ambition is, let's try to work with linear operators or matrices in finite dimension, if possible. And so the ambition of this work is very much to work with linear operators. And this is what Dexter did in his 81 paper as well. OK, so let's talk about higher order first. So now, suppose I want to curry this probabilistic adder. OK, so I want to curry with respect one of the two variables, let's say B. So as a probabilistic program, it will look like this. I still have my adder, but now I've got this curried adder, which takes one input and returns a function which expects the second input. Okay, and this is what this partial thing does in Python. Okay, so it's just the usual currying operation. Now, because I want to work with linear operators, I'm faced with this problem that the category of vector spaces is not Cartesian closed. I would like to go from the top picture of the adder to the bottom picture. And more generally, I want to curry in this way. Okay? Unfortunately, there are two problems. The first one is that if you look at the type on the top, I'm only covering product measures. Okay, so I'm only looking at certain very special input distributions. By no means do I cover all the possible input distributions. But worse than that is that it just doesn't work. It's going to break scalar multiplication. Vector spaces are not Cartesian closed. Okay? So there are two strategies. And I have to stress the fact that this not Cartesian closedness plagues any sensible semantics you can come up for probabilistic programming languages. It's not just this matrix semantics, it's any semantics. So the first strategy is to say, okay, I really want Cartesian closedness. So what I'm going to do is to create a new mathematical universe, which is Cartesian closed, in which I can somehow encode the probabilistic objects that I'm interested in. The second strategy is to say, okay, vector spaces are not Cartesian closed, but they're monodal closed. So why don't we do the currying with respect to this monodal operation instead of the Cartesian product? So in this work, which is the second strategy, most of the literature has followed the first strategy. Okay, so then it becomes really straightforward. At least in finite dimension, it's completely transparent what happens. We have the very nice property that joint distributions on 2 cross 2 are isomorphic to the tensor product of the measures on 2 times the measures of 2. So R to the 4 is isomorphic to R to the 2 tensor R to the 2. Okay, and so we have this very simple translation. And then in this setup, the adder is just the stochastic matrix I showed you earlier. And it's super easy to curry. You just do the maths, and you have everything in terms of operators. And you don't break anything. You don't break scalar multiplication because you're working with tensor products, not with Cartesian products. Okay, so it's really straightforward. Okay, so I've shown you a very easy finite dimensional case. Things are much, much, much harder for bigger spaces, infinite dimensional spaces. But the key ideas are the following. So to move from vector spaces to something called ordered Banach spaces. So this is a more general concept where there's a notion of norm and a notion of order. Okay, and this includes all the familiar spaces of measures that you can think of. Okay, and the order is important because we want to give a semantics to things like while loops, and that's why we need an order structure. But it will turn out to have a lot of benefits to include this order. Then we want to go from matrix to a more general concept, which are positive linear operators. Okay, so it's just the infinite dimensional extension of matrices. And then the really difficult part is that we want a tensor product for these ordered Banach spaces. And to give you an idea of the difficulty of this problem, the question of determining what the tensor product of Banach spaces should be was the thesis of Grothendieck in 1955. So this is really difficult maths, okay? But mercifully, Grothendieck has done it for us. Okay, as I said, the order structure is to interpret while loop. And so the result is a category of these ordered Banach spaces and linear operators, which is a model of intuitionistic linear logic. Moreover, we have an exponential comonad, which allows us to also reason classically if we want, still with linear operators. And the bonus, conceptually, it's not immediately obvious, at least, that the order structure that we have on these guys allows us a really clean semantics for the next bit of the talk, which is conditioning, Bayesian inference. Okay, so I'm going to return to my probabilistic adder. And remember, there was a mystery Bernoulli distribution in it. So I was sampling from something I didn't know. And suppose I want to learn this mystery distribution. Then the standard way is to use Bayesian inference. Okay? And the underlying mathematical concept is the concept of conditioning, which I'm going to present now. Okay, so as a model, this is how we would, it's a very simple way of writing how we're going to learn this mystery distribution. So the model adder is the generative model that we saw in the previous talk. And this is one step, the learn adder function is just a one-step Bayesian inference. So I have a prior, I do one observation, and I update my posterior. Okay, and I'm using the observe keyword as in Anglican. Okay, so how does it work? Well, first of all, now one of the parameters lives in 0, 1, okay? So now I'm in the discrete setting anymore. I need to say what the operator does on the measures on 0, 1. Okay, and this is the standard definition of what the semantics of this generative model should be. Okay, so it just averages out the model over the input distribution mu. Okay, now we're going to try to use Bayes' law. So this is the very naive, basic formulation of Bayes' law, which is deficient in many ways. But let's try to use it. So here, this probability of a pair of bits given one parameter of the model, I'm just going to write it as the function model adder. And the reverse gadget, which given an observation of 2 bits, gives me a distribution on the parameters, I'm going to just write it with a dagger and the symbols, the inputs permuted. Okay? Now I've got this quotient by Pij, the probability of one particular bit combination. And as we've seen in the first talk, this division can cause trouble. Okay? So I'm just going to move it on the other side. Okay, where I think it's safe. And then the final thing to do is to give a meaning to these probabilities, because here the probability of a parameter in 0, 1 is going to be 0. So in general, this formulation doesn't mean anything. So the proper way of writing it is like this. Okay, so this is Bayes' law, but written, as I would say, properly. Okay, and notice the interchange between these two. You said there's a kind of duality going on between these two operators. But the model adder dagger is the gadget I'm looking for, okay? And in this formulation, in this case, I can compute it explicitly because the measure here has a finite support, and so I can just do the quotient as I would normally do. Okay, so this is how Bayes' law gives us a gadget that updates the parameters, okay? Now, the really neat bit is this, in our semantics, in our mathematical universe, the operator model adder, which models the generative model, has a completely abstractly defined adjoint which works in the opposite direction, okay? And moreover, this completely abstractly defined operator that works in the opposite direction is precisely the denotation of the gadget I'm looking for. Okay, so that means that fundamentally I don't have to resort to Bayes' law, at least abstractly, to define what it means to compute the conditioned version of a program. Okay, it comes kind of for free from the mathematical universe. Okay. So the paper contributions on conditioning are the following. So the order structure, which I said earlier, turns out to be really, really useful, allows us to define special types, which we call Bayesian types. So Bayesian type is just a normal type together with a prior. So the prior is embedded in the type system. Okay? And these Bayesian types are interpreted as L1 spaces, which are the most natural spaces you could think of in measure theory. Okay? And Bayesian inference in this framework is just taking an adjoint operation between L1 spaces. So again, it really feels like the right maths to be doing this kind of thing. Moreover, this setting of linear operator between L1 spaces allows us to have access to a wealth of results in ergodic theory. And ergodic theory is what allows us to reason about these MC-MC algorithm, which we saw in the previous talk, okay? Because they have, the convergence is essentially an incarnation of ergodic theorems. Okay, so one side advantage of this formalism is that we are in the right mathematical universe to prove MC-MC algorithms very naturally. Thank you.
Okay, thanks, Fred. Questions from the audience?
So if you take this monoidal closed structure, do you lose contraction or weakening? That's my first question. Second question is, the category of measurable space also has a monoidal closed structure. And is there any relationship between that category and yours? Because typically people explain probability measure in terms of, by dualizations, they explain it in terms of the linear operator, right?
So the answer to the first question is yes and yes. It's really a linear system that you get. But because we have this exponential comonad, we can reason classically through the back door, but not naturally. It's fundamentally a linear system. And the answer to your second question is I don't know, but it seems highly plausible on the face of it. I don't know.
Okay, I'm going to read a couple of questions from Slido. Is your semantics of probabilistic programming with Banach spaces and tensor product no longer monadic?
That's a good question. Formally it's not monadic, but whether it could be just lifted, right? But I'm not. I would be afraid of saying something stupid, but yeah, let's just say it's not monadic. I also like the fact that we're thinking of these things in a different way.
Okay, I'll take more questions from the audience.
So there is semantics for probability in terms of commutative C-star algebras. Now, this seems like a relaxation of that. How do the approaches relate?
It's a universe I don't know at all, but I suspect that we might be doing similar maths in different languages. I'm not entirely sure. This is all real vector spaces, so that might be a bit different.
Okay, I'll continue with a comment from Slido that Saheb Jaromi published their paper 2 years prior to the Hexacosan. So I think someone in the audience wants to point out that maybe some historical inaccuracy has happened.
I stand corrected.
Okay, I'll take another question from the audience.
Could you compare this with the work on cones, positive cones?
Yes, so now we've got quite a few different approaches to probabilistic programming, to the semantics of probabilistic programming, and the work on cones by Thomas Erard and Christine Tassot and Michael Pagani is definitely the closest. And my intuition is that if we work at the detail precisely, they have the linear, the nonlinear fragment, and we have the linear fragment, and these two should come together. That's my hunch.
Okay, one more question from the audience, if you'd like. And if not, then let's thank Fred again.